So in the previous lecture we discussed algebra of matrices, and we defined algebraic operations for matrices like addition and multiplication. And we discussed that multiplication is not commutative, I mean matrix multiplication. So we had an example showing that the product of matrices A by B, and B by A, that they have almost nothing in common. But in fact, that's not completely true, just because there are characteristics that are the same for those matrices. And so now we are going to discuss one of them. So the others will be discussed later within the frame of this course. So 1.5 is the trace of a square matrix. So definition. Let A be a square n by n matrix. Then the sum of all elements along its principal diagonal is called the trace. So the sum where I ranges from 1 to n of A sub I is called the trace of A. So the most common notation is just TR of A. In some books there is a bit old-fashioned notation SP of A that comes from German Spur, so which is trace in German. But we will use this notation. So the trace is just the sum of all elements along the principal diagonal. And let us prove a simple proposition that for any matrices A, B of the same order, the trace of A multiplied by B equals the trace of B by A. So we see that these two matrices are not completely different. So let us prove this statement. So the proof is very straightforward. We need just to compute the trace in the left-hand side and the trace in the right-hand side. So the trace of A by B, just by the definition, equals the sum from 1 to n, A multiplied by B sub I. And then we need to write down what is the product of the two matrices. So here we have the sum from 1 to n, and here we have another sum where j ranges from 1 to n as well, and so we get A sub ij multiplied by B sub ji. So this is exactly this exactly follows from the definition of the product of the two matrices. And then I'm going to change the order of summation. So here we have two summation, one over I and the other one over j. So I can rewrite this sum as summation by j from 1 to n, then summation by I from 1 to n. And I'm going to change the order of these two elements. These are just numbers, so they commute. So I can write it as B ji multiplied by aij. Okay, and so now I keep the first summation, and the expression here is just the jth element of the product of the two matrices. So this is B by A, J. right? So this follows from the definition. And so here we have the trace of the product of the two matrices in the reverse order. So this proves our statement, and we see that the trace is the same for those two matrices. Okay, so what about the product of more than two matrices? So let us make this remark. So the trace of A multiplied by B and then multiplied by C equals trace of C multiplied by A by B. Why? Just because we can group those matrices, so I can just consider the first two matrices as, their product as some other matrix, and so here we have the product of AB by C, and here we have the product of C by AB. So it follows from the previous statement. So this holds for all matrices, for all A, B, and C from the set of matrices, from the set of square matrices with real entries. But this does not mean that we can consider any permutation of matrices here. So the trace would be different. So, but not every permutation of factors preserve the trace. So let us consider some example. I will take, so in particular, trace of A, B, C is not equal to trace of C, B, A. So let us try to verify this by some particular example. So consider matrices A. So I'm going to consider the simplest case, 2 by 2 case. So A would be something like 1, 2, 1 minus 1. So B would be, B would be 3, 1, minus 1, 1, and C would be 2, minus 2, 3, 1. Okay, and let us try to compute those products. So what is A by B and then by C? So I'll first multiply these two matrices. So 1, 2, 1, minus 1 by 3, 1, minus 1, 1, and then multiplied by 2 minus 2, 3, 1. So we get, what do we get here? 3 minus 2, which makes 1. Then 1 plus 2, which makes 3. Then 3 by 1 plus 1 by 3 plus 1 makes 4. And then we have 0 here, so this is the product of the first two matrices, and then we need to multiply this product by the third matrix. So we get 2 plus 9, which makes 11, then minus 2 plus 3, which makes 1. We actually do not need this number for computing the trace, but just to have the full picture, I will do these computations. So, and here I'm going to have minus 8. Okay, so the trace of ABC equals 3. Okay, and what about the product in some other order? So C by B and then by A. So as we discussed at the previous lecture, matrix multiplication is associative, so I can multiply any pair of them first. So 2 minus 2, 3, 1 by 3, 1 minus 1, 1, and then by a 1, 2, 1 minus 1. So what do we get here? So 6 plus 2 makes 8, then 0 here, then 3 minus 1, also 8 here, and 3 plus 1 makes 4. So 1, 2, 1 minus 1. So we have 8 here, and then we have 16 here, then we have 8 plus 4, 12 here, and how much? 16 minus 4 makes 12 here, if I'm not mistaken. So the trace of CBA is 20. So we see that the traces are different in this particular example. So you see that we can just invert the order in a product where there are two factors, but not in the general case. Okay, so this is a very important characteristic of a matrix, of a square matrix, and we will use it on many occasions within the frame of this course. And so now we are going to move to the discussion of linear systems, and we'll see how all these things with matrices can be applied here. So the second topic here would be linear systems. And so the first subtopic, 2.1, I will call it matrix representation of linear systems. So first of all, let us define what is linear system or system of linear equations. So system of equations of the form a sub 1, 1 times x1 plus a sub 1, 2 times x2 plus etc. plus a sub 1m times xm equals b1, a sub 2, 1 times x sub 1 plus a sub 2, 2 times x2 plus etc. plus a sub 2m times xm equals b2, etc. a sub n1 times x1 plus a sub n2 times x2 plus etc. plus a sub nm times xm equals bn. So the system of such equations is called a linear system. So here all x's are unknowns and a sub ij are coefficients. And a sub ij are coefficients. So now we will consider systems with real coefficients, but in general we can consider systems with complex coefficients, or maybe some, or coefficients could be elements of some other fields. So we will not discuss this in details, but nevertheless, so right now we know only real numbers. We will discuss complex numbers later. So let us consider systems of linear equations with real coefficients. Okay, and so the important thing is that we can represent such a system in a matrix form. So I will formulate this as a proposition, but so actually it is completely obvious that so system, I will call it L for its linearity. So system L is equivalent to the following matrix relation. So A multiplied by X equals B, where A is the matrix of coefficients, A sub 1, 1, etc., A sub 1, M, A sub 2, 1, etc., A sub 2, M, A sub n1, etc., A sub nm. So where M is the matrix of coefficients. So this matrix is usually called the matrix of coefficients. So I will underline this in green. So X is the column of unknowns. And B is the right-hand side vector. B1, etc., Bn is the right-hand side vector. So the proof is more or less obvious, just because if we multiply this matrix by this vector, we will get this form of thing. So when we multiply a matrix, which is matrix with n rows and m vectors, by a column vector, we get a column vector whose entries are computed in exactly in this way. So this means that the product of these two matrices is equal to the column vector that is in the right-hand side. So this is more or less obvious. Okay, so this matrix is called the matrix of coefficients, and along with this matrix we are going to consider another matrix. So the matrix A vertical line B is called the augmented matrix of the system L. So we have the matrix of the system that is denoted by A, and we have the augmented matrix where we just add the column of right-hand side. So this is the notation for convenience, and we will use both of these matrices further. Okay, so we introduced linear system, and we discussed how linear system can be represented in a matrix form, and now we will define the notion of elementary row operations. 2.2 elementary row operations. Okay, so I'll first define them, and after that we'll discuss why this makes sense to consider such row operations. So, definition. So, operations with rows of matrices of the following kind are called elementary row operations. So we will just list those kinds of row operations. We will have 3 of them. So E1 would be multiplication of a row in a matrix by a constant. By a non-zero constant, this is important. By a non-zero scalar. So this is one of the types of elementary row operations. So another type is swapping any 2 rows in a matrix. And the third type is addition better to say it slightly another way, addition of a row multiplied by a scalar to another row of a matrix. Okay, so we have 3 different types of elementary row operations. So we can multiply a row by a non-zero element, we can swap any 2 rows, and we can add 1 row multiplied by a constant to some other row. And these operations are called elementary row operations. So, of course, these elementary row operations change the matrix. So we do some operations with matrices. So after we apply these elementary row operations, of course, the result would be not equal to the matrix, to the original matrix. But the important thing is that we can apply these elementary row operations to linear systems. So maybe I will give one more definition before I formulate the proposition. So definition, linear systems are called equivalent if they have the same sets of solutions. Okay, and so now we'll prove a simple proposition that So this proposition states that when we apply elementary row operations to the augmented matrix of our system, the new system is equivalent to the previous one. So let A tilde B tilde be a result of a series of elementary row operations applied to augmented matrix of some system. Then the systems AX equals B and A tilde X equals B tilde are equivalent. So this proposition is almost obvious. Let me just write a few words as a proof. So we will consider these elementary row operations just one by one, and we need to understand that they do not change the solution set. So what about the first type of elementary row operations? So what happens to the system when we apply this kind of transformation? We just multiply an equation. We just take some row of our augmented matrix, and multiply it by a scalar. So this means that we take some equation and multiply this equation by a constant. So this does not change the equation. So transformations of the first type multiply the whole equation, multiply equations, better to say, by non-zero constants, which preserves the solution set. Okay, so what about the second type? So in the second type, we swap the two rows. So this is just this corresponds to the change of the order of equations. This also does not change the solution set. So transformations of the second type change the order of equations. So this also does not change the solution set. And what about the third type? So here we take one row of the augmented matrix and multiply it by we take a row multiplied by a constant and add it to some other row of our augmented matrix. So in this case, we also get the equation that is equivalent to the previous one. So for the third type, we add one equation of our system multiplied by a scalar to another one. So this also does not change the solution set. So all elementary row operations preserve the solution set, and that's why the initial system, the initial linear system, is equivalent to the linear system that we get after a series of elementary row operations. So this proves our proposition. Okay, so now we will discuss one special form of matrices, which is called row echelon form. So this would be 2.3. So 2.3 row echelon form. So we'll start with the definition. Non-zero matrix has a row echelon form if the following requirements are satisfied. So all 0 rows are at the bottom. So this means that if there is a 0 row and a non-zero row should be above every 0 row. So every non-zero row should be above a 0 row. And so the first, or maybe better to say not the first, but the leftmost non-zero element in every row is strictly to the right of the first non-zero element in the previous row. So we have these two requirements. So I will underline the notion that is being introduced here, so the notion of row echelon form. So we have two requirements. Sometimes the terminology is slightly different, so sometimes one more requirement is added here, but we will add it to the next definition that we'll have in a couple of minutes. Then, so I wrote here that non-zero matrix has a row echelon form, so we can call a zero matrix also a row. We can say that it has a row echelon form. This also depends on the terminology, but we will not need zero matrices in our considerations, so I just tried to exclude them, but that's not essential. Okay, so anyway, let's first consider some examples. So 1, 2, 0, 3, 4, 0, 1, minus 1, 2, 3, 0, 1, 2, minus 1, 1, 0, 0, 0, 0, 0. So this matrix does not have a row echelon form because here the first requirement is satisfied. Here we have a 0 row at the bottom of the matrix, but in the third row and in the second row, the first non-zero elements are just one above the other, so this is not reduced row echelon form. Oh, sorry, not row echelon form. We did not define reduced row echelon form yet, just because here we have these two elements. Okay, and now I will give an example of row echelon form. So 1, 2, 0, 3, 4. I'll take the first row from the previous matrix and the second one as well. So 1 minus 1, 2, 3, then 0, 0, 0, 2 minus 1, 0, 0, 0, 0, 0. So this is row echelon form, just because here we have the first non-zero element in the first column, here we have the first non-zero element in the second column, and so here we have the first non-zero element in the third column. So these are first non-zero elements in every column, and we see that in each row this first non-zero element is strictly to the right from the first non-zero element of the previous column. So this is row echelon form. And so let us also say that the first this means the leftmost, the first non-zero element in a row in row echelon form is called the leading element. Okay, so this is the first definition, then now we'll need another definition, so definition of reduced row echelon form. So non-zero matrix has reduced row echelon form if it has row echelon form then all leading elements are equal to 1, and finally in every column that contains some leading element, this element is the only non-zero element. So this is called reduced row echelon form. Okay, so what does this mean? That we add two more requirements to our to the previous definition. So we require that all leading elements should be equal to 1. So this is not satisfied here because here we have 2 as the leading element in the third row. And we add one more requirement, that if some column contains a leading element of some row, for example here the first column contains the leading element in the first row, the second column contains the leading element in the second row, then the third column does not contain any leading elements. So it's free of leading elements, and that's why the third requirement is not applicable to this column at all. And as well as for the last column, right? So there are also no leading elements in the last column. And here, if we look at the third requirement of this definition, so we must check it for the first column, for the second column, and for the fourth column of our matrix. And we see that it is not satisfied just because these leading elements are not the only leading elements, are not the only non-zero elements in these columns. So here we have 2 besides 1, and here we have 3 and 2 just above the leading elements. So this is not reduced row echelon form. And so now we will consider more examples of reduced row echelon forms. So one more example. One, 0, 1, then -1, 3, 0, 0, 0, 0, 1, 0, 0, then 2, 3, 4, 0, 0, 0, 0, 0, 1, 0, 0, 0. So this matrix has reduced row echelon form. Let us verify this. So I'm going to draw this staircase-like structure as in the definition. So these are the leading elements. And we see that the first, the second, the fourth, and the sixth columns of these matrices, they contain leading elements in some rows, and so the third requirement of our definition is satisfied here, just because above these leading elements we have only zeros in this matrix. So this is reduced row echelon form. And if we go back to the previous example, so this is row echelon form, but not reduced row echelon form. Okay, so we introduced these important notations, and now I'm going to formulate and to prove a theorem that is being used in order to solve linear systems. So, theorem. Every non-zero matrix can be transformed to row echelon form by a finite series of elementary row operations. Okay, so let us prove this theorem. Okay, so first step would be to move all zero rows. If we have some zero rows, we can move them to the bottom of our matrix by applying the second type elementary row operations. All zero rows to the bottom by applying transformations of type 2. Okay, So consider the leftmost column of our matrix, so I will denote it by A, of A, that contains a non-zero element. So it can happen that a number of columns at the left of our matrix are zero columns, so we consider the first non-zero column of our matrix, and so contains a non-zero element, and denote its row by J. So what does this mean? That we have some matrix, and so here probably we have, or possibly we have, a number of zero columns. Then we choose the first non-zero column, so we also can have zeros in this column. But somewhere here we have some element. I'll denote it by C. That is not zero, so contains a non-zero element C. So, and we have something else here. Okay, so, and this element C is in the jth row of our matrix. So what can we do? We can first swap this row with the first row, and then multiply it by, or divide it by C, so multiply it by 1 over C. Or we can first multiply it by 1 over C and then swap with the first row. So 3 divide row J of A by C and swap with the first Okay, so after having done this, we were going to have something non-zero there in the first row. And what else do we need to do? So I will sketch this. So we possibly have a number of zero rows here. Then we have 1 here, so we divided our row by C, so we have 1 instead of C here, and we moved this row to the upper position. So we have here 1, and then we possibly have some non-zero elements here in this column. Okay, so what are we going to do next? If there are non-zero elements in the jth column of A below 1, then we add the first row multiplied by an appropriate constant, to all these rows. So our aim is to get rid of all these elements. So, for example, if we have 2 somewhere here, but then we can just add the first row multiplied by -2 to this row, and this will transform our matrix into such a form that we will have only zeros there. So when we do this, so after having done this, we'll have only zeros below 1 in the jth column of our matrix. Okay, so our matrix will look like, so here we possibly have some zero columns, then we have 1, then we have zeros here, and then we have something to the right of this column. And what do we do next? We will consider this submatrix and apply the same arguments to this submatrix. And so by doing this, we will move to the right, and finally we will arrive at row echelon form of our matrix. So I will denote this A prime, and so we will apply this procedure to A prime. Okay, so as I have already mentioned, we need to consider the submatrix A prime and apply the same procedure to it. So finally we will get row echelon form. So we can mention that in general we applied all types of elementary row operations. So here we had to divide our row by some number, then we swapped rows, and then here we also applied the third type of elementary row operations in order to get rid of non-zero elements in this column. Okay, so this is how it works. And let us discuss another row echelon form, reduced row echelon form. So it is also possible to transform every matrix to reduced row echelon form. So I will formulate it as a separate result. So we proved this theorem, and one more theorem. So every non-zero matrix can be transformed to reduced row echelon form by a finite number of elementary row operations. Okay, so proof is very similar to the proof of the previous theorem. We just need to continue this procedure. So assume that A has row echelon form. So it exists according to our previous result. And moreover, if we look at the proof, then just as a benefit, we have ones as leading elements in all the columns except maybe for the last one. But anyway, if the leading elements are not 1, if some leading element is not 1, we can divide this row by an appropriate constant, and so we get the second property of the definition satisfied. So, first, if necessary, divide rows by constants, or multiply, maybe I'll better say multiply. Multiply rows by constants in order to meet the second requirement in the definition of reduced row echelon form. Okay, and what's next? So now we have this staircase structure. And we have leading elements that are already equal to 1. And what do we need to do? We need to get rid of all the elements above these 1s. So how to get rid of them? We can since we have 1 in every column that contains a leading element, using this row we can add a row multiplied by an appropriate constant to get rid of all the elements above this leading 1. So fix some leading element by applying E3, I mean these elementary row operations. We can kill all the elements above. So for example, if this star is 3, then we need to subtract the second row multiplied by 3 from the first one, and we will get 0 there. And so this leads to reduced row echelon form. So I think I will not go into more details. This is more or less clear that such a procedure leads to reduced row echelon form. Okay, and so now we have this tool, and we're going to apply this tool for solving linear systems of equations. So the next topic, the next subsection would be Gaussian elimination. So consider a linear system. A times x equals b. So here I use the matrix notation and transform the augmented matrix to row echelon form A tilde B tilde. So it's possible according to one of these theorems. So denote by R the number of non-zero rows in the matrix A tilde. And now let us look at the augmented matrix. Then the number of non-zero elements in the augmented matrix is either R or R plus 1. So why? If we assume that there are more non-zero rows, this means that there will be non-zeros in the right-hand side, and this contradicts the definition of row echelon form, because we will have first non-zero elements in the rightmost column, and there will be two of them, just one, at least two of them, just one below one, and this contradicts the definition of row echelon form. So we can state that there are two different options. So either in the augmented matrix we have some additional non-zero row, or we do not have it. So, and now we are going to consider several cases. So the first case, assume that the number of non-zero rows in A tilde is R plus 1. So we have R non-zero rows in the left part of our matrix, and we have one additional non-zero row in the right-hand side part. So here we have this staircase-like structure, and we have one additional step there. So we have something here, and we have some element B tilde R plus 1 here, and it is non-zero. So what does this mean? So let us look at the equation that corresponds to the R plus 1 row. So it has form 0 times x1 plus 0 times x2 plus etc. plus 0 times xr according to our definition, times xm, just because here we have only zeros. And this equals B tilde R plus 1. So we see that this equation has no solutions, just because we have 0 in the left-hand side and non-zero element in the right-hand side. So there are no equations, there are no solutions here. Okay, so we see that there are no solutions here, and since this system is equivalent to the original one, there will be no solution for the original system. So since this system has no solutions, the system AX equals B has no solutions as well. So we have already proved that the systems that are obtained one from the other by a finite number of elementary row operations are always equivalent. Okay, so this was the first case. So in the first case we have no solutions. Okay, now assume that the number of non-zero rows in the augmented matrix is equal to R, so these numbers coincide, so we do not have this extra step there. Assume R equals M, which is the number of unknowns. So what does this mean? This means that, so M is also the number of columns. So since M is the number of columns, we can see that we have, in this case, we have a leading element in every column. Okay, so this means that our matrix has this kind of form. So we have just steps here. So the number of non-zero rows is equal to the number of columns, and this means that we have this staircase structure, and the length of each step equals 1, right? So we are going to have something like this. So we have non-zero elements here. Non-zero elements. And step length is 1 everywhere, just because the numbers are the same. And possibly we can have some 0 rows at the bottom. So they affect nothing just because corresponding equation looks like 0 equals 0. So we can have any number of these equations. They are not important. Okay, so what about this case? Let us go from the bottom to the top. So consider the last non-zero equation. It has the form A tilde sub m multiplied by xm equals b tilde m, right? Just because here the number of rows and columns are the same. So this equation has this form, and we know that this element is non-zero. So we can find xm by dividing by this coefficient. Okay, so now we know the the last unknown, so we substitute substitute the value of this coefficient to all other equations. Okay, so let us look at the previous equation. Then all other equations do not depend on xm, just because we have already eliminated xm, so they depend only on x1, etc., xm minus 1. So consider the last of them. It has the form a tilde m minus 1 times x m minus 1 equals something. So we do not know that because we cannot say that we have exactly this element here, just because we did some other manipulations when we eliminated xn, so we get something else there possibly. So this equation has the form, has this form, and since this is the leading element, it is different from 0, and so we can eliminate xm minus 1, and so on. So continue to do this. To obtain the solution. And so note that in this case the solution is unique. Why? Just because every equation allows us to find find corresponding unknown just without any options. We just divide by this coefficient and we get some particular value. So the solution is unique in this case. Okay, and so the last case is when the number of non-zero rows is still equal to R in the augmented matrix, but here we assume that m is greater. So assume the number of non-zero rows in the augmented matrix is R, but m is greater than R. So this means that now the step length, at least somewhere, is greater than 1. Somewhere is greater than 1. Okay, so what does this mean? But still, we can eliminate leading variables starting from the bottom. Of A. So we repeat the same procedure, but with the only difference that if somewhere the step length is greater than 1, then our leading variable can be expressed not only in terms of the numbers that are here, but in terms of the other variables that are in between. So what do I mean? So I will just consider some, maybe not the particular case, but consider some local part where the step length is greater than 1. So what does this mean? That we have this we have something here, we have something here, and I'm going to denote this column by J1 and this column by J2, so let J2 be greater than J1 plus 1. So this corresponds to the fact this corresponds to the case where the step length is greater than 1. So we can eliminate x sub J1. So this means that we express it in terms of x sub J1 plus 1, x sub J1 plus 2, etc. So in terms of all the elements that are here. So therefore the solution is not unique because elements xj plus J1 plus 1, xj1 plus 2, etc. that are not leading can take any values. To tell the truth, I did not yet define the leading variable, but I mean the variables that do not correspond to leading elements of the matrices of our matrix. So in this case, we get in this case the solution of this system is not unique, and since the systems the transformed system is equivalent to the initial one, the solution of the initial system exists but is not unique. So we described the three possible options. So the first option is that this system has no solutions, that linear system has no solutions. The second option is that it has unique solution, and the third option is that the solution is not unique. So it is more or less obvious that if the solution is not unique, then we have infinite number of solutions, just because we have the variables that can take any values, any real values. So this means that the number of solutions is infinite. Okay, and so this procedure is called Gaussian elimination. So definition. It's called Gaussian elimination. So it is called elimination just because we eliminate variables one by one, starting from the bottom, and we see that it is essential that our matrix has row echelon form here, because otherwise we cannot start this elimination here. We cannot start this elimination from the bottom. So we use the theorem that any matrix can be transformed to row echelon form using elementary row operations. Okay, so this is how it works in theory, but a bit later we will consider a number of examples. But first, so let me start the next section, the next subsection, 2.5, using reduced row echelon form. So now we will see that if we use reduced row echelon form instead of row echelon form, then in some cases, or maybe in most of the cases, it is more convenient just to get the solution of our system, or to get solutions of our system explicitly. Okay, but so first maybe I will need to give some more definitions. So definition, so any solution of our linear system L, that was in the beginning, is called a particular solution. The collection of all particular solutions of L is called the general solution. So sometimes general solution consists only of one particular solution. So this happens when the solution is unique, as we've seen before. But in general, general solution consists of infinite number of particular solutions, and so we just collect all particular solutions in this case. Okay, then one more definition. So L is called consistent. If it has solutions. And it is called inconsistent otherwise. So if we go back to these cases, so in the first case here, our system is inconsistent because there are no solutions. And in the second case and in the third case, it is consistent just because it has solutions. So in the second case, it has unique solution, but in the third case, it has infinitely many solutions. Okay. So now we'll consider a couple of examples. And I'm going to demonstrate how reduced row echelon form can be used for finding solutions of linear systems. So the first example would be the following system of linear equations. So I will write it as a system first. So 2 times x1 plus 5 times x2 minus 8 times x3 equals 8. Then 4 times x1 plus 3 times x2 minus 9 times x3 equals 9. Then 2 times x1 plus 3 times x2 minus 5 times x3 equals 7. 1 times x1 plus 8 times x2 minus 7 times x3 equals 12. So consider these simultaneous equations. I'll check the coefficients. Okay, so I hope that I copied everything in a correct way. So this system is equivalent to the following matrix representation. So I'm going to consider just the augmented matrix. So it contains all the information about the system. So 2, 5, minus 8, and then 8 here. 4, 3, minus 9, and 9 here. 2, 3, minus 5, 7. 1, 8, minus 7, 12. So all the information about the system is encoded in this augmented matrix. And now we're going to apply elementary row operations in order to transform this system to first to row echelon form and then to reduced row echelon form. So what am I going to do? First, I'm going to swap the first and the fourth rows, just in order to put one here according to the procedure in the proof of one of the theorems. So we keep the second row and the third row unchanged. And we have 2, 5, minus 8, 8 here. Okay, so then our strategy is to get rid of all the elements below the leading element here. So this is the leading element, and we need to get rid of all these elements here by an appropriate elementary row operation, by applying appropriate elementary row operations. So what am I going to do? So I will apply several elementary row operations at once. So first of all, I will subtract the second row, the third row multiplied by 2 from the second one. So our row 3 minus 2 times row 2 minus 2 times row 3. Then I will consider the difference of row 4 and row 3, so row 4 minus row 3, and finally row 3 minus 2 times row 1. So application of these 3 elementary row operations will produce zeros everywhere below this one that I circled in blue. So I keep the first row unchanged, 1, 8, minus 7, and then 12 here. Okay, and so what do I get here? 0, then 3 minus 6, which makes minus 3, I guess. Then minus 9 plus 10, which makes 1. And then 9 minus 14, which makes minus 5. Okay, so then here I take the third row and I subtract the first row multiplied by 2, so I get 0. Then 3 minus 16 minus 13. Then 5 minus 5 plus 14, which makes 9, I think. And then 7 minus 24, which makes minus 17. Okay, and finally here I consider the difference of the two rows. So I have 0, then 2, then minus 3, and 1. So this is what I get here, and so we see that we have one element here, and so now we need to work with this part of our matrix. So it is convenient to have 1 somewhere. So first of all, I will add, or 1 or minus 1. So I will add the fourth row to the second one. So R2, row 2 plus row 4. And I will keep, at this step, I will keep all other rows unchanged. So we have 0, then minus 1, then we have minus 2, and then we have minus 4, I think. Okay, so we have 0, then minus 13, then 9, then minus 17 here, and 0, 2, minus 3, 1. So this is what we get here. So the only difference is in this row. Okay, so let us proceed. And now we have a convenient tool to get rid of elements here. So we have, so this element would be the leading one, and so we are going to get rid of the elements here. Okay, so what does this mean? So I will maybe, it is not convenient to multiply this row by 13 maybe, because I will get something nasty here, and so I keep the first row unchanged, and then so I keep the second row unchanged as well. 0, minus 1, minus 2, minus 4 here, and then I will add the fourth row multiplied by 6 to the third row, so I get 0, minus 1, then 9 minus 18, which makes minus 9, then so minus 17 plus 6 makes minus 11, so 0, 2, minus 3, 1. Okay, so then we consider the difference of the third row and the second one, so row 3 minus row 2, and row 4 plus 2 times row 2. So we keep the first two rows unchanged here. 12, 0, minus 1, minus 2, minus 4. Then we get 0, 0. Then minus 9 plus 2, minus 7. Then minus 11 plus 4, minus 7 as well. And then here we have 0, 0. Then minus 3 minus 4 minus 7. and minus 1, sorry, 1 minus 8 minus 7. So here we have two rows that are the same. We can consider their difference, and we will get a row of zeros here. So row 4 minus row 3. So 1, 8 minus 7, 12. And then 0 minus 1 minus 2 minus 4. Or maybe I will, for convenience, I will multiply this row by minus 1. So minus 1 multiplied by row 2, and I will also multiply the third row by divided by minus 7, so we get 0, 0, 1, 1, and 0, 0, 0, 0. Okay, so this is row echelon form. And recall our discussion of possible cases. So here the number of non-zero rows in the matrix A is the same as the number of non-zero rows in the augmented matrix. So the solution exists. And in the previous consideration, in previous theoretical consideration, we just had to eliminate variables going back, starting from the last one. But a more convenient way is to use more elementary row operations in order to transform this matrix to reduced row echelon form. And we'll see how it works now. So what am I going to do? So I'm going to first to get rid of elements here. So we have these leading elements. So we are lucky that all of them are just ones. We do not need to perform additional actions in order to make them 1. Okay, and so I will add the third row multiplied by 7 to the first one, and I will subtract the third row multiplied by 2 from the second one. So we get 1, 8, 0, and here we get 12 plus 7, which makes 19. Okay, then we have 0, 1, 0, and 4 minus 2, which makes 2, and we have 0, 0, 1, 1. And so I will not write this row of zeros because it contains no information. So I can just get rid of this row. And so what do we have here? So we have the only element that we need to kill in order to transform this matrix to reduced row echelon form. So in this case we just subtract the second row multiplied by 8 from the first one. So we get 0, 0, 0, 19 here, then 0, 1, 0, 2, 0, 0, 1, and 1, sorry, not 19, but 19 minus 16, which makes 3. I have forgotten to do this with the last element in the first row. Okay, so this is what we get here. And what system is equivalent to this matrix representation? So we get a very trivial system, which is exactly its solution. So we have x1 equals 3, x2 equals 2, x3 equals 1. So we get the solution. we get the solution here. And so I would like to stress that here that in this particular case, and so this happens in the general case when you have the identity matrix here, you just get the solution here in the right hand side. So you see that we do not need to make some elimination of variables going backwards from the last one. We just get the solution in the explicit way. So the solution here is written in the right hand side. Okay, so now we will consider another example of a linear system that demonstrates that behavior of a linear system, maybe better to say, of the solution of linear system can be different. So the second example, here we are going to consider the system, another system. I will write it in the matrix form just to save space. So the augmented matrix of the system would be 1, 2, 1, 0, 2, then 1, 1, 3, 2, minus 1, 4, 2, 2, 1, minus 1, 3, minus 2, minus 1, and the last row 2, 0, minus 2, 3, 1, and 1 in the right hand side. Okay, so this matrix corresponds to a linear system with 4 equations and 5 unknowns. I'll double check everything. Okay, so let us write down the general solution. Let us find the general solution of this system. So I will apply elementary row operations. I'm going to keep the first row unchanged, 1, 2, 1, 0, 2, and then 1 in the right hand side. And then, so we will apply several elementary row operations at once. So I will subtract the first row from the second one. So I'm going to get 0, 1, 1, minus 1, 2, and 1. Here then I'm going to subtract the first row multiplied by 2 from the third one. So this would be 0, then minus 3, then minus 3, 3, then minus 2, minus 4, minus 6, and minus 1, minus 2, which makes minus 3. Okay, so this is the third row, and finally we're going to subtract the first row multiplied by 2 from the fourth one. So we get 0, minus 4, then minus 4, then 3, then minus 3, and minus 1. So I hope that's correct. And so we have 1 here, and we need to get rid of elements here. So we can first, maybe it makes sense just to divide the third row by minus 3. So I get 1, 2, 1, 0, 2, and 1 here. Then 0, 1, 1, minus 1, 2, 1. So 0, minus 1, minus 1, 1, minus 2, and minus 1. And then I'm going to, so I multiply the third row by 1/2, and I subtract, I add the second row multiplied by 4 to the first row, so I get 0, 0, one more 0, and so 3 minus 4, which makes minus 1, and minus 3, plus 8, which makes 5, I guess. Okay, so 4 minus 1, that's 3. Okay, so this is what we get. Then one more step is to get rid of minus 1 here. So 1, 2, 1, 0, 2, 1 in the right-hand side. Then we keep the second row unchanged as well. Then 0, 0, 0. So 3 zeros here. I subtract the, I add the second row to the third one. So I get 0 here as well. So I get, so I could have noticed before that they are proportional, so I get the row of zeros here, and so I get 0, 0, 0, 1, minus 5, and minus 3 here. Okay, so I need to swap these two rows in order to get a row echelon form, and I would like to continue making elementary row operations in order to make reduced row echelon form. So 1, 2, 1, 0, 2, 1, 0, 1, 1 minus 1, 2, 1, then 0, 0, 0, 1, minus 5, minus 3, and then the row of zeros. So this is a row echelon form. But not yet reduced row echelon form, because we have non-zero elements above the leading ones. And so now I will proceed with more elementary row operations. So I need to get rid of this element first. So I get 1, 2, 1, 0, 2, and 1 in the right-hand side. So I add the third row to the second row. So 0, 1, 1, 0, minus 3, and then minus 2. So I get, I keep the third row unchanged. And so then I have a row of zeros. So this is not yet the reduced row echelon form, because we have 2 here above the leading element, and so we need to apply one more elementary row operation. So I'm going to subtract the second row multiplied by 2 from the first one. So I get 1, 0, minus 1, then 0, and then 2 plus 6 makes 8. So 1 plus 4 makes 5. And 0, 1, 1, 0, minus 3, minus 2. 3 zeros, 1 minus 5 minus 3, and the row of zeros. So finally we get the reduced row echelon form of our matrix. And now I'm going to write down the system of equations that correspond to this augmented matrix. So we come to the system x1 minus x3 plus 8 times x5 equals 5. This is the first equation that corresponds to the first row. Then x2 plus x3 minus 3 times x5 equals minus 2. And x3 4 minus 5 times x5 equals minus 3. So this is the system that we obtained here. And what can we do? We can express some variables in terms of the others. So I can write down the general solution. So the general solution has the form, so x1 equals 5 plus x3 minus 8 times x5, then x2 equals minus 2 minus x, should be plus here, minus x3 plus 3 times x5, and x4 equals minus 3 plus 5 times x5, and here x3 and x5 can be arbitrary. They are arbitrary real numbers. Okay, so we get the solution of this system. And so here we express some variables in terms of the others. And so I'm going to give one definition. So consider a linear system Ax equals b, where A has a row echelon form. Then the variables that correspond to leading elements are called leading variables. And all other variables are called free variables. Okay, so in our example, variables x3 and x5 are free variables, and variables x1, x2, and x4 are leading variables. And the general strategy is to express leading variables in terms of free variables. So So if our matrix has the reduced row echelon form, then the procedure to express the leading variables in terms of free ones is more or less automatic, like in this example. So we just move everything to the right-hand side besides the leading variables, and all the coefficients are ones just because of the definition of the reduced row echelon form, and so we get the general solution. And every particular choice of free variables corresponds to some particular solution of this linear system. So, for example, if I set x3 to be 1 and x5 to be 4, I get some particular solution of this system. Okay, so here we see that there is principal difference between this example and the previous one. So in the previous one we had unique solution, and here we have infinite number of solutions just because we have free variables, and these free variables can take arbitrary real values. And so if the system has no free variables, then it is, and if it is consistent, then it has the unique solution. So this is how it works, and the important thing is that once we have the reduced row echelon form, then we can automatically write down the general solution. Okay, so we'll stop here, and so at the next lecture we will continue to discuss other things, and we will prove the existence, the uniqueness of the reduced row echelon form. Okay.